Let's reiterate the main points we've learned on page 23 of the PowerPoint. First, if the population is a normal distribution, then whatever the sample size, the sample mean will be normally distributed. Second, even if the population is not normally distributed, but if it's close enough to normal, then if the sample size is at least 30, we're okay. Third, if the population is very different from being normally distributed, if it's highly skewed or there are outliers, then so long as the sample size is greater than 50, then we're okay, and we can use the normal distribution for the sample mean. Hence, a large sample size is very helpful. But not quite always, because let's look at page 22. Remember these equations? We can use the one on the left if the population is finite. We can use the one on the right if the population is infinite. The one on the right is very much easier to remember and use. The nice thing is that we can use that if, look at the first bullet point, if small n over big N is less than 5%. Hence, if the population size is large relative to the sample size, we can use the simpler equation on the right to compute the standard deviation of the sample mean x bar. Let's now look at concrete examples. Remember this. Let's assume that the 900 applications for St. Andrews College are normally distributed. Let us now ask this question. What is the probability that if we draw a simple random sample of 30, that the sample mean x bar will be between 1080 and 1100? We already know two things. First, that the mean of the sample mean is equal to the population mean, which is 1090. We also know the standard deviation of the sample mean x bar, and just refer to the previous equation. Hence, we know that the sample mean x bar is normally distributed, and anything that's normally distributed, as you remember from chapter 6, can be converted to standard normal. So as you remember from chapter 6, in order to calculate the probability of a normally distributed variable being between two values, we first calculate the upper bound and then the lower bound. Hence, first calculate the probability that the sample mean will be less than 1100. And this is just the procedure you follow. First you convert 1100 to a z-value, and we already know the population mean, which is therefore the mean of the standard deviation, and we also know the standard deviation of the sample mean, 14.6, from page 22. Hence we can convert it to a z-score of 0.68, and the area to the left of that is 0.7517, which you can see from any standard normal table, which you will also find in your textbook. Second, now look at the probability that the sample mean will be less than 1080. And again, you first convert it into a z-value, which in this case is minus 0.68. And in this case, the area to the left of minus 0.68 is 0.2483. Therefore, the area in between z 0.68 and z minus 0.68 is just the area to the left of 0.68 minus the area to the left of negative 0.68, and therefore it's 0.7517 minus 0.2483. Hence, what we can say is this: there is a 50.34% that the sample mean score will be between 1080 and 1100. Please take a minute or so to reflect on what we've been doing and confirm that it is consistent with what we've been doing in chapter 6. Here is now an illustration of why the sample size is important. Suppose we now draw random samples of 100 instead of 30. And let's again ask the same question. What is the probability that the sample mean will be between 1080 and 1100? Please take note. Remember from page 23? Remember the formula for the standard deviation? And remember that the sample size small n is in the denominator. Hence, the larger is the sample size, the smaller the standard deviation of the sample mean will be. But also remember, the smaller the standard deviation of the sample mean, then the larger will be the z-score. And hence, the larger the z-score, the larger will be the probability that we will be between 2 points. This is concretely conveyed in the last bullet point of this page. Look at the standard deviation. It's now 8, whereas before it was 14.6 when the sample size was 30. What happens is that the sample mean becomes more tightly distributed around its expected value, which you can see in the orange line. And this is numerically what happens. And therefore, look at the area between the 2 points. It's going to be larger. Specifically, there will now be a 78.88% chance that the sample mean will be between 1080 and 1100. Please play around with this. For instance, ask yourself this. Suppose we draw a random sample of 30. What is the probability that the sample mean will be between 1070 and 1110? Now try this problem. Suppose we draw a random sample of 100. What is the probability that the sample mean will again be between 1070 and 1110? Let's now move to the sample proportion, P bar. The logic is similar. We're trying to figure out what is the population proportion P. To answer the problem, we draw a random sample of small n elements. We measure the sample proportion population P bar, and we then use P bar to make inferences about P. Remember St. Andrews College. Again, these are the results we get. That the expected value of the sample proportion, P bar, will be equal to the population proportion. That is, P bar is an unbiased point estimator of P. Again, there are 2 ways to calculate the standard deviation of P bar. On the left is with a finite population, is on the right with an infinite population. And once again, if small n over big N is less than 0.05, we can use the simpler equation on the right. Please note, in the equation, we are using P, not P bar. Concretely, let's answer this. But before we do that, it's important to note these are the conditions required in order for us to use the normal distribution. First, NP has to be greater than or equal to 5. And second, N1 minus P has to be greater than or equal to 5. Let's look at that concretely. Recall this. Remember that 72% of the 900 applicants want to live on campus. Please keep that in mind. That is P. P equals 0.72. We now ask ourselves, if we draw a random sample of 30, what is the probability that the sample proportion will be between plus or minus 0.05 of the actual population proportion? That is, the question is, if we draw a random sample of 30, what is the probability that the sample proportion will be 0.67 to 0.77. First, what do we know about the sample proportion p-bar? Can we assume that it is normally distributed? First, let's look at this condition. NP. N is 30, P is 0.72, and the product is 21.6, which is greater than 5. We're okay. Second, N times 1 minus P. It's 30 times 0.28, which is 8.4. It's also greater than 5. Hence, we can use the normal distribution for p-bar. So we calculate the standard deviation of the sample proportion, which is 0.082. And as you will see, we're using the equation for the infinite population because 30 is less than 5% of 900. We also know that the expected value of p-bar is 0.72. So we're set for business. First, calculate the z-value at the upper endpoint. And remember the equation from chapter 6 is just equal to 0.77 minus the mean, which is 0.72, divided by the standard deviation, which is 0.082. That gives us z of 0.61. And the area to the left of 0.61 is 0.7291. Let us now go to the lower endpoint. Convert it to a z, and since the lower endpoint is 0.67, subtract the mean of 0.72 from it, and divide everything by 0.082, and we'll get minus 0.61. And the area to the left of minus 0.61 is 0.2709. Therefore, the area in between 0.61 and minus 0.61 is just the difference between the two areas, or 0.4582. Hence, we can answer the question this way. There is a 45.82% chance that a random sample of 30 will have a sample proportion between 0.67 and 0.77. Now try this if the random sample is 100, and you will see that the answer you will get will now be larger than 45.82%. The last section of the chapter describes several sampling methods. Please just skim through it because this may be important in your job or in your other courses, but we will not emphasize it in this course.